So we're going to talk about ions and ionic bonding. And first, before we go into the ionic bonding, we need to know for sure what ions are. Now remember, this staircase right here, this separates the metals from the non-metals. So that's going to be important to know when it comes to ionic bonding. Now, we're just going to do the A group. See these A's right here? We're going to do the A group because it's easier just for explanation purposes. You can get the idea because the transition metals right in here, they kind of play by their own set of rules. Now with the A group, if you notice, there is a Roman numeral in front of the A's. There's 1, there's 2, and then it goes across the board to over here on the right, 3, 4A, 5A, 6A, 7A, and 8A. Now the goal, if you think of this like a puzzle, the goal of the game is to have 8 electrons in the outer shell, and that's called the valence shell. So here's the nucleus, and here's a shell, and it has electrons in it. And here is the outer shell, and the goal is to have 8 electrons in the outer shell, because that would be complete. And that's just like the noble gases over here. The noble gases already have 8 electrons in their outer shell, so that's why they don't really play well with others, and they don't really do much mixing with other elements, because they're complete. They already have these 8 electrons in their outer shell. Now the outer shell is called the valence shell. It's the valence. And the electrons that are in the outer shell, oops, I can't spell valence. The electrons that are in the outer shell are called the valence electrons. So just as some background terminology there. So that's the valence electrons. Now here is a great little trick that you can do on the periodic table. As you remember, I just pointed out these Roman numerals, 1, 2, 3, 4, 5. For group A, as it goes across, 6, 7, and 8. Well, these Roman numerals are how many electrons are in that element's valence shell. So this is the number of valence electrons, and valence electrons are abbreviated VE. So this entire column right here, everything in this entire column has 1 electron in their valence shell. So 1 valence electron in their valence shell. So if you have a nucleus, they have 1 electron in that outer shell, like that. Now this group 2A is going to have 2 valence electrons in their outer shell. So here's the nucleus, here's their outer shell, and they're going to have 2 electrons in the outer shell. And if you go all the way across the periodic table to the rest of group A, here is Roman numeral 3A, so that's going to have 3 valence electrons. And this is going to have 4 valence electrons, 4 electrons in their outer shell. This is going to have 5 electrons in the outer shell, 6 electrons in the outer shell, 7 electrons in the outer shell, and we already said that the noble gases have 8 valence electrons in their outer shell, so they're complete. So that's a little trick that you can do. You can just look on the periodic table and it's going to tell you how many electrons are in these elements' outer shell. Now, let's start with something like sodium right here. Now sodium has one electron in its outer shell. It has one valence electron. So here's the nucleus. And here's all their shell layers. Here's sodium shell layers. And in the outer shell, there's only one electron. Okay? So the goal is to get rid of that electron so we can get rid of this whole outer shell. And so sodium would have just the inner shell, which is complete. The inner shells are complete with 8 electrons in it. Same thing over here for magnesium. Let's see magnesium. Magnesium has 2 electrons in its outer shell. One, 2. So magnesium wants to get rid of the 2 electrons from its outer shell, so we can just get rid of the entire outer layer there because it has no electrons if it gets rid of the 2, and we'll just be left with 2 energy layers, and we can just go ahead and assume that the energy layer beneath it has 8 electrons in it. So now it's complete. Because remember, the goal is to have 8 electrons in your outer shell. So if we had that third outer shell, if we had that third shell as an outer shell with the 2 electrons on it, we want to get rid of those 2 electrons and therefore that outer shell. So magnesium can end up with whatever outer shell it has. It has a complete set of 8 electrons. So what happens when you get rid of, when an element gets rid of an electron? These elements in their periodic table states have a 0 charge. And that's hydrogen have a 0 charge. 0 charge. But it wants to get rid of its 1 electron so it can be complete. So if the hydrogen with a 0 charge gets rid of 1 electron, and electrons are negative, remember, that's going to make that hydrogen positive, have a positive charge on it. Because, see, it had a 0 charge on it, but it gave away a negative electron. So therefore, it's going to have a positive charge on it. Now let's do the same thing with calcium right here. Calcium is in column 2, so it's going to have 2 electrons in its outer shell. So calcium has 4 energy shells, and I know that because it's the 4th row down. And on the outer shell, it's going to have 2 electrons. And before these new shells can happen, you have to have 8 electrons. You have to have a complete set of electrons on the shell beneath it. So calcium wants to get rid of those 2 electrons, and therefore this outer shell. So it ends up with three shells, but that outer third shell is going to be complete with 8 electrons. But what happens when calcium, which is normally a zero charge just by itself, what happens when calcium gets rid of 2 electrons? That's 2 negative charges. Calcium ends up with a positive 2 charge to it because we got rid of 2 negative charges and calcium was a zero charge minus the 2 negative charges, and that makes it positive, 2 positive. So calcium in its ionic state is 2 positive. And that's what an ion is. An ion is just an element that's given up or taken on more electrons, so it changes the charge from 0 to whatever its new charge is. Now let's do some on the right hand side. Remember this staircase right here? This staircase is going to separate the types of elements. So this is going to be non-metals, and this is going to be metals on the rest of it. And you'll need to know that here in a minute. But let's do oxygen. Okay? Oxygen is in column 6A, that Roman numeral 6. So that means oxygen has 6 electrons in its outer shell. It would be too much energy to get rid of all 6 electrons. You don't want to get rid of all 6 electrons because that's too much energy. That takes too much energy to get rid of all 6 electrons because it only needs 8 to be complete. So what it does is it adds 2 electrons in order to get 8 electrons on their valence shell. So if oxygen, which in the periodic table has a 0 charge all by itself, and you can count the columns to see how many electrons it's going to take on, how many electrons it's going to take on. There's one more column and there's 2 columns right here. So oxygen is going to want to take on 2 electrons plus its 6 that it normally comes with. It has 6 electrons when it has a 0 charge in its normal state. But if you add 2 more electrons, it's going to equal 8 electrons. So oxygen in its ionic state is going to be 2 negative because it added 2 more electrons, and electrons are negative. So oxygen in its ionic state, and that's an ion, it's going to be 2 negative. And that is the same thing for everything over here on this side of the staircase. Not the noble gases, because the noble gases already have 8. So not the noble gases, but everything else is going to add more electrons to it in order to get to that 8 electrons in their outer shell. And everything over here on the left side, these guys are going to give away 1 or 2 electrons so they can get back to 8 electrons in their outer shell. So these guys are always going to end up with a positive charge when they're in their ionic state, when they're an ion. And remember, an ion is just an element that has given up or taken on more electrons so it can have 8 electrons in their valence shell. So that's on the left-hand side, but on the right-hand side, these guys are going to add electrons, which is going to make them have a negative charge. Okay? Now, the positive charges over here on the left, those positive charged ions are called cation. And I always remember the cations are the positive charge because look, in the middle of cations, there's a plus. It's really a lowercase t, but still, you can look at that like a plus. So you know that the ions that are coming from the first two rows over here are going to be positive because they're going to give up electrons so they can have 8 electrons in their outer shell. Now, the ones that turn out negative as ions on the right-hand side, these are called anions. So cations over here on the left in the metals, and the non-metals will turn into anions in their ionic state. And that's just what ions are. Ions are just a regular old element that has given up or taken on electrons so they can have a complete set on their outer ring. They can have and the complete set is a total of 8 electrons. So that's for ions. So now let's look at ionic bonding. And this is pretty normal logic here. You shouldn't have any problems getting this. Let's do Na, for instance. Na is in group 1. 1 is in group 1A right there. So you know Na is only going to have one electron in one valence electron, one electron in its valence shell. So it's going to give away one electron to get rid of that extra electron in the outer shell. So if Na is normally 0 charge on the periodic table, but it gives away a negative electron, that's going to end up making it positive. So Na in its ionic state would be a cation. Now let's look over here. Let's look over here to Cl, with chlorine, on the right-hand side. Now chlorine is in group 7A. So it has 7 electrons around it. So it's easier for chlorine at a 0 charge to take on one more electron because it already has 7 in its outer shell. So it's going to take on one more electron so it has the complete set of 8 electrons. And that's going to give it a negative charge because it took on an extra electron. So here's where your extra electron goes. It makes it a negative charge. So we have Na plus and Cl minus. Now, what do charges do? The opposite charges attract. Opposites attract. Just like a magnet. And so just like a magnet, a positive Na floating around is going to end up sticking to the negative Cl. Because Cl has one negative charge to it, and Na has one positive charge to it. So those guys are going to swap this negative and this positive, and this negative and positive are going to make them stick together. And so they're going to equal out a 0 charge when they're together as NaCl. See, NaCl has 0 charge because that cancels out the positive and negative charges that Na and Cl have. So NaCl is going to be an ionic bond. And that's pretty much it. It's just a bond because the Na had a positive charge and the Cl had a negative charge, which attracted each other to each other, and when they fused together, that positive and negative is what attracts them to each other, and they cancel each other out, so they're now neutral again. They have 0 charge, and when they're in NaCl, and that's just table salt. That's sodium chloride. So let's do one more. Let's do calcium, which is over here on the left. Now calcium is in row 2A, so it has in its normal form, it has a 0 charge, but it has 2 electrons in its outer shell. So it wants to get rid of those 2 electrons. So that makes calcium, when it's an ion, have 2 positives, have a charge of 2 plus, and that's a cation because it's positive. Cat, see there's a plus in the middle of the word cation. And then let's see over here. Let's look at oxygen. So oxygen is in group 6A, so it has 6 electrons in its outer shell, and it's trying to get to 8 electrons in its outer shell. So oxygen plus 2 electrons makes it 8, gives it 8 electrons in its outer shell, but that gives oxygen a 2 minus charge because it has 2 extra electrons in there. So let's go down here to the calcium. Calcium has positive 2 charge. The oxygen has a negative 2 charge. So the negative 2 charge and the positive 2 charge attract each other, and they stick together. And together as calcium oxide, they would have a 0 charge because those two, negative 2 and the positive 2, cancel each other out. So it would just be calcium oxide. I have no idea if that actually exists in the universe, calcium oxide, but just for the sake of explaining, I just picked two random elements. So that's all there is to it, to ionic bonding. Now let's look at something a little bit more involved. Let's look at sodium right here and oxygen right here. Okay, now sodium is in group 1A, so it has an extra electron. When its charge is 0, it has 1 electron in its outer shell. So it wants to get rid of that 1 electron from its outer shell, so it has a complete set of 8 electrons on its outer shell. So that means Na is 1 positive. Now oxygen has, in its natural periodic table state, when it has 0 charge, oxygen has 6 electrons in its outer shell. So it wants to take on 2 more electrons so it can get to 8. So it has a complete collection of 8 electrons in its outer shell. So that's going to give it a negative 2 charge. So what do we do now? We have an Na with 1 positive, and we have an oxygen with 2 negative. So how do we put those together? Because these are different. Well, one way we can do that is if you end up having 2 NAs, if you have 2 NAs and each sodium has a positive 1 charge, that's going to equal a positive 2 charge because you add up the charges when you add up the sodium. And so Na2 is going to have a positive 2 charge. That is going to blend well with the oxygen's negative 2 charge. So you're going to end up with Na2O, sodium oxide, and that whole thing is going to have a negative, or is going to have a 0 charge because the positive 2 and the negative 2 cancel each other out. And that's pretty much it for ionic bonding. as far as the basics go. It gets a lot more involved than that, but this is what you need to know right now, because we're going to get into Lewis dot structures pretty soon. We're going to go into covalent bonding, and that's where you really need to pay attention. But this is sort of self-explanatory. But if you have any problems or questions, please feel free to call me.